Water, a fundamental element in our society. Water has been essential for civilization in both modern and ancient times. There are many uses for water, such as the manufacturing of goods, cooling, cleaning, transportation, recreation, cooking, drinking, and as a vehicle for transporting unwanted waste material from our homes and businesses. This video is intended to provide a glimpse into the process that is necessary to provide the clear, safe water that is so often taken for granted in our everyday lives. Potable water, or the water that is intended for our daily use, must undergo varying degrees of treatment before it is considered acceptable for consumption. The water sources for this potable water are divided into two main categories: surface water and groundwater. Groundwater is the precipitation that penetrates the surface of the ground and makes its way into the underground water table. Generally, the earth acts as a filter and removes particulate matter from the water as it courses through the various layers to aquifers. Aquifers are voids in the earth where water is trapped and held, becoming available for use through wells. Because of the filtering action referred to earlier, the groundwater usually has lower turbidity and less biological impurities than surface water sources. However, the groundwater may in turn dissolve more minerals as it contacts the various elements in the soils, and as a result, may have higher levels of minerals like iron and manganese, or radioactive materials like radon gas. For this reason, aeration towers are a frequent sight accompanying well sources. Aeration towers can remove volatile gases like hydrogen sulfide. They can also be used to oxidize iron from the soluble state into an insoluble state. Aeration towers may simply infuse air into the water, or they may also contain devices designed to disperse the water particles, which makes the aeration more effective. Depending on the geological formation surrounding the groundwater source, the water may need further treatment. For example, in areas that have a high limestone content, the water may need to be softened using an ion exchange unit. In other areas, the water may be exposed to carbon dioxide, which interacts with the water to give it a lower pH, making it more corrosive to the metal pipes in the distribution system. These waters may require some type of corrosion control treatment to make the water less aggressive. Some of the treatment options are to use a chemical like soda ash to raise the pH, or to use a phosphate product to line the walls of the distribution system. Some groundwater may also be considered under the direct influence of surface water. An example of how this might occur is that an abandoned well with the casing at or below ground level could channel surface runoff directly to an aquifer that also serves as the source for a nearby active well. Groundwater in this category may require treatment similar to a surface water source. Water treatment facilities and processes are as varied as the people they serve. They come in all sizes and shapes. Some treatment plants could be contained in a phone booth, while others occupy areas the size of several city blocks. Another common term is package plant. This refers to filtration plants that have all the required processes contained within one unit. Some of these units are small enough to be contained in a single room, producing hundreds or thousands of gallons per day. From the non-transient, non-community system adding calcium hypochlorite at a well source, to the water system that treats millions of gallons of river water and serves it to the metropolitan areas like Philadelphia and Pittsburgh, there are treatment plants designed to fit every need. In the process, These plants use everything from calcified remains of single-celled diatoms to chemicals containing salts and acids to pieces of coal, sand, and wood in an effort to provide safe, clean water to the customers. Some groundwater sources require no more than simple disinfection, while some surface water sources need multiple stages of treatment involving a variety of chemicals and pieces of equipment. Various filter types include multimedia filters, membrane filters, slow sand, and diatomaceous earth filters. The multimedia types are generally divided into two categories: conventional and direct. Conventional systems typically use the flocculation, sedimentation, and filtration sequence. The direct filters do not have the sedimentation stage. Direct filters can be utilized in applications where the source water turbidity is normally low. Direct filters are required to be tested or piloted at the source for at least 1 year before they will be issued a permit. Different types of direct units utilize a combination of flocculation or flash mixing, contact clarification, and multimedia filtration. One group of direct filters uses an upflow clarifier followed by multimedia filtration. In the upflow clarifier portion, differing types of media are used to trap most of the unwanted matter. The media types include plastic beads, sand, and garnet. In this process, the coagulant chemical is added before the clarifier. The clarifier portion is cleaned by backwashing or flushing with untreated water. As mentioned earlier, conventional filtration uses flocculation, sedimentation, and filtration processes for filtering the water. The purpose of the flocculator is to mix the coagulant chemical and the particulate matter, then to promote the contact and growth of these particles as they begin to adhere together. For this reason, flocculators often are staged in series. The idea is to make the floc particles dense enough to settle out in the next stage of the treatment, which is the sedimentation stage. If the plant is operated properly, most of the suspended particles have agglomerated together and are heavy enough to fall through the water and settle on the bottom of the settling basin. This sludge is removed from the basin periodically. It can be applied to drying beds to separate the water, or it may be run through a filter press to dewater it, or it may be hauled away for further treatment. Upflow clarifiers use a sludge blanket to trap particulate matter as the water passes through this blanket. These clarifiers are temperature sensitive and require raw water that has a substantial amount of particulates in order to build the sludge layer. The remainder of the particulate matter after the flocculation process is carried over onto the multimedia filter, where it is removed, allowing the clean water to pass through. The filters continue to process water until one of 3 set points is reached. The set points are the length of time referred to as run time, turbidity, and head loss. An increase in effluent turbidity may indicate that the filter is overloaded and unable to retain the particles. Head loss refers to the pressure differential between the top and bottom of the filter media. As the pore spaces are closed off with particulate matter, the pressure loss increases. Whenever any one of the 3 criteria is reached, the filter is backwashed or cleaned, and the process is started again. Other types of filtration include diatomaceous earth, DE, membrane, and slow sand, in the DE application, either a vacuum or pressure is used to adhere the DE to the filter plenum. There are normally several plenums attached to a manifold. Plenums are covered with a permeable material that allows the free flow of water. DE is the skeletal remains of single-celled plants called diatoms. There are differing grades of DE based on pore size. Usually, the pore size on the plenums is matched to a particular grade of DE. To start a filter run, DE is added to water. Enough DE is added to evenly coat the entire surface area of the plenums. This is referred to as the pre-coat. As the water is drawn or forced through the filters, the particulate matter is trapped in the pore spaces of the DE. As the available pore spaces are closed off with the particles, the head loss begins to increase. To offset the rate of increase on the head loss, a constant supply of new DE, known as body feed, is added to the water. This body feed extends the runtime of the filters between cleanings to maximize the amount of water processed before filters reach their design head loss and require cleaning. The used DE is simply rinsed off with moderate pressure from a hose and can be regenerated or otherwise disposed of. One noticeable advantage of the DE filtration is there are no chemicals required. Normally, DE filters are used where the source water turbidity is low and not prone to sudden spikes. Another type of chemical-free filtration is membrane filtration. The membranes are manufactured hollow fibers. The fibers can be made to various pore sizes. Depending on the nominal pore size, the particular type of filtration is referred to as micro, nano, ultrafiltration, or reverse osmosis, RO. The reverse osmosis process is used to desalt seawater and in the manufacture of pharmaceuticals, which requires a high-quality product. These fibers are bundled in tubular units, and there may be any number of units in the filtration train. The more water required, the higher the number of units used. Slow sand filters are yet another chemical-free filtration option. The process utilizes beds of sand, normally about 35 inches deep. On the surface of the sand bed, a biologically active layer develops known as the smutch deck. This layer provides an excellent addition to the sand media to trap and remove unwanted material from the water. As the smutch deck grows, the available pore spaces diminish until the water flow is restricted enough to warrant cleaning. Cleaning is done by skimming or otherwise removing the upper portion of the smutch deck. This material may either be disposed of or regenerated. One drawback to the slow sand filtration is the relatively large amount of surface area required to compensate for the slower flow rate. Conventional and direct filters normally have a flow rate of about 4 gallons per minute per square foot. On the other hand, the typical rate for slow sand is about 1/2 gallon per minute per square foot. All three types of chemical-free filtration are capable of removing particles in the size range of Giardia and Cryptosporidium when properly operated. Another benefit is the diminished threat of disinfection byproducts. Disinfection byproducts, also known as DBPs, are a result of natural organic matter found in the water combining with chlorine to form trihalomethanes, THMs, and/or haloacetic acids, HAAs. They are both considered carcinogenic substances, and water systems are required to meet maximum contaminant levels on each. From the time the water vapor in clouds begins to condense and fall in some form of precipitation, it begins to pick up impurities from the atmosphere and continues the process whether it becomes surface water or groundwater. Most of the water used today requires treatment to make it potable for consumption. There are a variety of treatment options available, from the simple disinfection to the more complex reverse osmosis process. Regardless of the complexity, the treatment system is only as good as the operator using it. Water treatment plant operators at every level need to be diligent and conscientious as they go about producing the best drink in town.